Now we have to step back and see what the consequence of that is for causing the flow to accelerate as it moves up the conduit. We think about this, the big effect of the bubbles expanding is to cause the density to decrease, right? If we go back here, if we go back, we started with something that was 100% liquid, or maybe 99% liquid, with very few bubbles in it, and we end up with this dusty gas, which is 98, 99% gas, and just a few clots of magma in it. So there's a huge decrease in density as this fragmentation process occurs. So what we're going to see now is that when that density decreases, it necessitates the velocity of the flow to accelerate. So here we have a sort of a schematic diagram of a conduit. This is what magma is moving up the conduit. And for simplicity, we'll assume that the radius of the conduit is constant. So it's a cylinder of radius r. We'll call v the average velocity of that flow. So what's driving the flow upward is the difference between the pressure in the magma chamber. There's some pressure down here. And at the very top, we have atmospheric pressure up here. The pressure in the magma chamber is much greater than the pressure at depth, and so that's forcing magma up the pipe. What's resisting the magma from flowing is both gravity, right, the density of the melt, and viscosity. So those two effects are resisting the tendency for flow to occur. The mass discharge rate, which I'm going to label Q here, is the area, which is pi r squared, times the velocity, the average velocity that the magma is flowing, and the density of the magma. That's the amount of mass that passes through each cross-section in a unit of time. And if we have steady flow, as indicated in this box, flow doesn't need to be perfectly steady, but we can approximate during an eruption that the flow is steady, then this mass discharge rate, Q, is constant. And that means Q is the same at all depths in this cross-section. But we start here at great depth. The rock is, the magma has very small bubbles, so the density is high. The density is really high down here. And as we go up and it fragments, the density decreases very dramatically. So if the density is going to go down, in order to keep this product the same, right? If the density goes down and Q is staying the same, and we're assuming that the radius of the conduit stays the same, then the velocity must increase. So the velocity, the melt moving up the pipe has to speed up because its density is going down. And you can think about this maybe in a sort of a human context. If we imagine a lot of people walking through a narrow hallway or a tunnel, and if you were all packed in shoulder to shoulder, walking at a slow pace, and then when you reached some point, I said, well, now you have to be arm's length apart. Well, obviously the people in the front would have to speed up to get away from their neighbors if they're going to be arm's length apart. So that's like the density going down. The people at the front will have to start running. And if now I say you have to be 10 feet apart or 20 feet apart, you'd have to really run even faster to get your effective density to decrease. Your speed would have to go up. So that's really basically what happens in explosive eruptions. The speed of the flow accelerates as the density decreases. We can see that in cartoon form here in this slide on the left. We start with the liquid. We have nucleation of the bubbles. We have what's called bubbly flow. Magma is moving upwards. The bubbles are expanding. We reach this surface here where fragmentation occurs, and it goes from a magma with gas bubbles to a gas with magma fragments. This becomes a very turbulent flow. It tends to move at extremely high speeds and will erupt out of the top of the volcano. So down here is nucleation. Right? This may or may not equal the point at which the solubility is met, depending on whether the melt gets supersaturated with respect to the gas or not. So these are some calculations that are done for this kind of a conduit. And this curve here, which I'll try to highlight, shows the gas volume fraction. That's going from 0 to 1, so 0 to 100%. And you can see that gas volume fraction increases until we reach the fragmentation depth, gets very high, and then it will keep increasing towards 100%. The viscosity can change at that point, but I think we won't worry about that today. So this just emphasizes that point that I was getting to a minute ago, that the saturation and the exsolution or nucleation depth don't have to be the same. If you have homogeneous nucleation, that is with no crystals, the magma could become saturated at this depth, but stay supersaturated for some point until the bubbles actually nucleate. And then the fragmentation surface, where the bubbles actually fracture the bubble walls, and we go from a liquid to a gas. With heterogeneous nucleation, lots of crystals, lots of imperfections, no supersaturation, then the saturation depth and the exsolution depth will correspond. So saturation is when it's thermodynamically favored for the bubbles to form. The exsolution is when they actually do form. I mean, that's distinct from fragmentation, where the bubbles are actually breaking apart. So lastly now, I'll just show some calculations I did with a numerical code to illustrate typical behavior for two kinds of eruptions. One's a Hawaiian eruption, a basaltic eruption, and the other will be from Mount St. Helens. So these calculations were done for a typical Hawaiian eruption. The conduit is pretty thin. This is the conduit radius in meters. And I only did two runs here, one in red and one in green. And it's a little hard for me to even see here, but the temperature of the lavas are on the order of 1250 degrees centigrade. That's the same in both cases. This is basalt, so it has relatively low silica content, on the order of 50%, and they're about only 3% crystals. The only thing I actually changed in this calculation is how much water is dissolved. So in the red curve, there's relatively little water dissolved, and in the green curve, there's twice as much, I think 0.3 and 0.6 weight% water. So we see on these plots pressure as a function of depth. So this is depth going down in the conduit, the volume fraction of gas, the velocity in meters per second, and the Mach number, which is just the speed relative to the sound speed of the liquid. So if we look at the relatively dry case, the red one, you can see that the bubbles don't start forming till we're very, very close to the surface. This is 1,000 meters, 1 kilometer depth. So you can see we're within 100 meters of the surface, that water's coming out of solution, we're getting a bubble phase to form, and that volume fraction of bubbles is getting up to almost 70% by the time we reach the surface. As the volume of bubbles increases, that causes the speed of the flow to accelerate, and that brings the Mach number. It never gets to 1, so there's never a shock wave that forms in this instance. If there's twice as much water present, that's the green curve here, then we reach the exsolution point at a deeper level in the conduit. There's more water, so it comes out of solution at higher pressure. That causes the flow to begin accelerating sooner, and we get to somewhat higher velocity at the surface. And it's this acceleration that, as you see in the picture here, that leads to these very high fountaining phases. You can see the helicopter here for scale. In some high fountaining phases of the Hawaiian eruptions, the lava will be jetting up to 1,000 feet in the air. And what's driving that is the water dissolved in the magma. That's the key point. It's that water that's expanding that's getting it to rush out. And what always happens in these eruptions is the very early part of the eruption is rich in gas, and so the high fountaining phase is like this. This was probably taken back in 1983 when Pu'u'u was just forming. The early phase of the eruption is very rich in gas, and so you get the spectacular either curtain of fire or high jetting phases like this. As the eruption goes on for longer periods of time, we're now 30 years into this eruption, and at this point, the gas, the water, and the CO2 are able to percolate up through fractures in the earth, and so by the time the magma gets to the surface, it's very degassed, it's very dry, and it flows out nice and smoothly at the surface. You don't get any high fountaining anymore. You only see this in the very earliest phases of the eruption. Okay, so that was a Kilauea eruption. Here's a Mount St. Helens eruption. Now to do this one, I needed to take a wider conduit. Why? Because now we're talking about dacite. And so now we're talking about something that has 72% silica content and it has 27% crystals. So the viscosity is many, many thousands of times larger than it was in the Hawaiian case. Temperatures are a little bit lower, 900 degrees. So all these parameters are kept the same. Again, the only thing I changed in these is how much water is dissolved. The first case shown in the orange curve is only 0.2%, then 1.6, 3.3, and 5 weight percent water. And we'll just see how the flow is expected to differ depending on how much water is dissolved. So in the very dry case, the orange curve, well, first of all, this is pressure, again, velocity, density in this case, and the volume fraction of gas. You can't see the orange curve here because the volume fraction of gas is always 0. So the density stays high, the bubble phase doesn't form, at least until very, very close to the surface. The density stays essentially high, the flow never speeds up, it stays at low speed. So this would lead to a lava flow. This would lead to no eruption, no explosive eruption. Now in the green case, the green curve, we have 1.6 weight percent water, and you can see what happens. We reach the exsolution point there. A separate gas phase forms. I think in this numerical code it doesn't allow any supersaturation. See, the volume fraction of gas is increasing up to about 70%, at which point the magma fragments. When it fragments, the density goes way down, and the speed accelerates to the point where it's now something like coming out at 50 meters per second. If we jump all the way to the purple curve here with 5 weight percent water, which is not actually an unreasonable number for Mount St. Helens. And by the way, this is going down all the way to 8 kilometers, so it's much, much deeper. It's a much thicker conduit. You can see in this diagram where the fragmentation surface is occurring. At this kind of concentration, we have some water that's exsolved, forming a bubble phase all the way down at 8 kilometers, but you can see that bubble volume fraction expanding very dramatically until we reach the fragmentation surface. The melt is going to fragment here. It's going to turn into a dusty gas. The density will drop very dramatically, and you can see this accelerating up to something like 150 meters per second, where it's shooting out, it's jetting out of the conduit at this very, very high speed. So that gets the magma shooting out of the volcano in what we call the gas thrust region. The gas thrust region is where the flow out of the volcano is inertially driven. It's driven by the kinetic energy of these bubbles expanding. Surprisingly, the gas thrust area is not all that high. There will be some ballistic blocks that will be shot out, some heavier fragments that will come flying out. But most of it's jetting up in the atmosphere as long as it's not too dense and we don't get column collapse and pyroclastic flow. In this convective region here, The flow is convecting around and it's drawing in ambient atmosphere. That ambient atmosphere is interacting with the hot pyroclasts, these hot little ash fragments, remember, that used to be the walls of the bubbles that are now broken up. All that heat started out at 900 degrees centigrade is causing the air to heat up as it's entrained, and so all this convective swirls are going on, causing this to rise buoyantly, not because it's being thrust, but because it's actually just like a helium balloon rising up in the air. Eventually it gets to some height where it's neutrally buoyant, and then you get the umbrella cloud spreading out. So we'll have a little simulation to show this later.